Okay, here's data that I have collected with the pendulum. Your file is going to look somewhat like that. I'm going to open it up. It's going to look like this. First thing I do, I need to make sure that I have the solver add-in installed. So to do that, I'll go to File, Options, and then go to Add-ins, and where it says Manage Add-ins, I say Go, and make sure Solver Add-in is checked. And then I press OK. The way the spreadsheet comes out, that's the raw data. This is information about your phone. And this is information about when the data was collected. I'm going to paste a picture for information here. This is the way the phone is configured. The y-axis is along the length of the phone, the z-axis is perpendicular to the face, and this is the x-axis. Now the acceleration sensor is configured this way, where we have acceleration along the z, y, and x. Okay, so this one is going to be pointing this one. Okay, so this is our data. If we look carefully here, I'm going to double click here. This is the acceleration along the x, here the acceleration along the y, z, and the overall magnitude. What we are going to do is check which one of these is going to work for us. Usually, whenever you are going to work with data, you don't mess with your raw data. So I'm going to come here and copy that sheet. Create a copy. I'm going to make it, put it here, and raw data too. So I'm going to play with this. I'm going to save before continuing, so if it crashes, I don't lose my work. And the first thing I'm going to do, I'm going to highlight these three with the time. So I highlighted that part and then Control-Shift-Down arrow to highlight all the data. We have 30,691 data points, so it's a lot of data points. And I'm going to go here, Insert, and I'm going to select a chart, Scatter. Okay, and here's the data. Okay. Now in this particular case, okay, just to move it to the top, I'm going to do Ctrl-X to cut it. And I'm going to move to the top here and paste it here. Okay. Now this is showing us all of them. Okay, I'm expanding it so we can see. First thing to note is I actually collected lots of data. This is probably the start before I start collecting data. This looks like a part where I collected good data. Now, where does that happen? It happens probably at the start of about 80 seconds. And it stops at about 110 seconds. So that's the data I'm going to focus on, between 80 and 110 seconds. I'm going to delete the rest for this data here. So to do that, I'm going to come here. Since it's a lot of data, it's a little difficult otherwise to delete what we need. So I'm going to come here, Time, go Data, and Filter. And I'm going to click here. Okay, so this shows all the data points. So what we are going to do here, select this, and we tell it less than And we talked about 80 seconds, so we're going to tell it 80. And OK. So what it is going to do here is just show us the data up to 80,000. It's going to delete this graphic if I'm going to leave it here. So I'm going to do Control X to delete it myself. And I'm going to come here to the second row and highlight it by clicking here. And then Control Shift down arrow, so that will highlight all those rows. And I'm going to right click and delete rows. And then I'm going to come here and tell it clear filter from time. And come here, Control V to paste back my graphic. And you notice the graphic is missing the data before the 80 seconds now. I'm going to do the same thing, but now for the data above the 110. Okay, so I'm going to come here, do the same thing, but greater than and 110. And I'm going to say, okay, I don't see the graphic because it's up there. I don't have to worry about preserving it. Highlight the first row I see, Control Shift down arrow key, I highlight all of them, and right click and delete row. And then I come here, clear filter, and I see everything, and this is my graphic, and I have only the data I want. Now what I'm going to do here, I'm going to click on this axis, right click, format axis. And instead of automatic here, I'm going to tell it, let's start at 80. Okay, so it went from 80 to 115. We can tell it 110 if we want. Okay, let's see, 110. Okay, and we can tell it what divisions do we want. Okay, now this has selected for us the data that we want. And these graphics here are to help us navigate the data, see what we have. We are not using it yet for any analysis. So I'm not worried about adding the labels and everything. This sheet now is our new raw data. It has only the data that we are interested in. Okay, this is the graph we have obtained. Look at the different curves, 3 of them. One for the x, acceleration along the x, one for the acceleration along the y, and one for the acceleration along the z. The blue one along the x looks like it's a damped sine function. Same thing for the gray one. It's a different story for the orange one. So what we are going to do, we are going to ignore the orange one. We are not going to look at it, but we are going to look at the gray and the blue. So to do that, I'm going to first delete this here, this title, so it makes things a little bit more visible to us. I'm going to delete the magnitude of the acceleration because it's also no use for us. So I highlighted it and pressed delete button. Okay. Then I'm going to copy this sheet several times and use it once for X and once for Z. But before doing that, I'm going to add some more information here. Let me start by pasting the equation that we have in the handout, the lab handout, that describes the acceleration as a function of time. This is the expression, so let's enlarge. So what we are going to try to do is fit our data that we measured to this equation. To do that, I'm going to define these quantities, A sub n, B, and square root of G over L and beta. I'm going to define them here. Let's say A sub m, so AM, B. The other one I'm going to call it omega, and the other one I'm going to call it beta. And I'm going to come here below, and I'm going to give them names. Acceleration M, enter, and dampen B, and then omega, and then beta. And I'm going to set up some arbitrary values, not 100% arbitrary values for these. So for example, for A sub m, since we are seeing values here that are below 1 from the data that we have, I'm going to put something that's like 0.8. And for B, I'm going to put a small number, 0.05. For omega, omega is 2 pi over the period. So the period here, so if I go from here to the next one, it looks like we are going from about, this is 80, this is 85, so this looks like 83, so that looks like 2 seconds. So 2 pi, that's 6 over 2, so that looks like at about 3.5. So I'm going to put 3.5. And for beta, I'm going to just put an arbitrary number 5. Now these are startup values that I'm putting there. Now that I have that set up, I'm going to copy my sheet. Create copy, and I'm going to copy it here. And I'm going to change this and call it X. So I'm going to keep AX there. But the others, I don't need them. In here, instead of the AY that we are not going to use, I'm going to type AC for calculated A. And I'm going to change this one to AX. So it is shorter. Okay. Now here, what I'm going to do is use this formula here. So I'm going to write equal. It's going to be A sub m, so click here. Then times exponential of minus bt. So I'm going to put parentheses, exponential to the power, parentheses, minus b times t is coming from column A. And close the parentheses and close the other parentheses. And that's times sine of omega times t again plus beta. Close the parentheses and hit the enter key. Okay, we have a small error here. I think my error here is with the E. I believe it is supposed to be EXP, exponential and parentheses. Okay, so I think we are covered now here that I corrected it. Okay, perfect. So here is the calculated value. So I'm going to double click here. where we have the box. Okay, so you notice here it changed that orange curve for us. Perfect. Now the next thing I'm going to do is right-click on the graph, select data, and we are going to remove this altogether. Now, instead of here, we are going to calculate the square of the difference between these two. Okay, so I'm going to come here, equal, parenthesis, this minus this, and the square. And I'm going to do that, copy that for all the data. And then I'm going to come here and write equal and add all these differences. So I'm going to write sum and put my cursor here, Control Shift down arrow, so it will highlight all of the data. And close my parentheses, and that's the sum of all squares that's in the bottom, on the top here. Okay, now the fun part. So I'm going to come data here, and on the right you see we have the solver here. So I click on solver. Since I had my cursor here, it already selected E3. We are going to select minimum, and we are going to come here, click on this one, and select these cells where we have the data that we would like changed, and check this. So when we press solve, what the solver is going to do is going to change these values so the curve will become a better match to the blue one. The orange will become a better match to the blue one. Okay, we'll press solve. Okay, and you see that's what we got. And it asks us if we should keep the solution or not. Okay, we're going to tell it okay. Now the fit provided these parameters: 4.2 approximately, 0.019, 2.7, and 41. Now, of course, there are uncertainties with these. We are not going to try to calculate them as part of this lab. However, omega here is supposed to be the coefficient in front of t, this square root of g over L. G being 9.8 meters per second squared, L is the length of the pendulum. So we can solve for the length of the pendulum from this value here. So if we square this, that would be the square of this, that would be G over L. So L is going to be G over the square of this. So if we write it here, that's going to be equal to 9.8 over this squared. Okay, that gives us about 1.32 meters. So this length, I need to compare it to the length that I actually measured in the lab and find the percent difference between them. That can be an indicator of how good my fit is or how bad it is. Another thing I could have done, I could have timed the pendulum, timed, let's say, 20 oscillations, and found the period from that. 20 oscillations, time for 20 oscillations divided by 20, that gives me the period, and compare it to the period that we get out of here. to pi over omega. Now I can do the same analysis by checking the z-axis. And to do that, all what I will have to do is the same thing as this, but for z. The way I'm going to do it, I'm going to duplicate this, the last one we did, call it z, and then come here and copy the z data and come here and paste it here. Okay, so this is a sub z. Now I'm going to change the name of these to make sure we are fine, so that we're not using the same value as we had in the other one. So I'm going to call that, I'm going to add z there. So add z, and then add z here, add z here, and add z here. And come to my equation for the calculated A and add z's in front of each one of these. Z, 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 and Z. And copy that equation. Okay. Now, of course, it didn't change anything because they are the same values. But then notice how this value, the sum of the squares, is big. Now, when we run the solver, it's going to try to minimize this. So solver, okay, it's collecting the same kind of information, f to I. Okay, everything is set. So we tell it solve. Okay, and this is what it gave us. So it's a different value for this. Slightly different length, but not very different. Okay, and it minimized the sum of the squares to about 70. And if we are satisfied, we tell it it's okay. Now, if we feel like this is not pretty good and we can improve it a little bit, we can act on these values. One more thing sometimes that we end up having to do, if this is a function that's supposed to be symmetric above and below the zero, and if my data is not symmetric, if I have more data above the zero than below, I might need to shift it by adding a number or subtracting a number to this and then simulate that shifted data. Essentially, where's your origin? So this is a way to collect data from the pendulum.